Okay, let's begin lecture, or let's begin our session. We're going to do some review of electromagnetic induction for a few minutes using the eye clickers, and we're going to extend what you already know into something new that I want to emphasize, all of it related to electromagnetic radiation. That's our special topic for today and also Friday. By the way, I'm working on getting a lab experiment for everybody, for hopefully for Friday, using coils and electromagnets and bar magnets and stuff like that. So you'll have to be patient with me on that. But let's do some electromagnetic induction clicking. Get your clicker ready. The first few are multiple choice. So just click in and answer. Line of current I comes out of the plane toward you. A dot. No, Thomas, no. You're doing it deliberately now. Because I saw you using the right hand, and he went like this to fake me out. But I know your tricks now, Thomas. All right, go ahead and make a count. $15 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. What? Oh my goodness. Everybody voted for counterclockwise? So that means like this? Go ahead and sketch that in. It's a couple more. Way further out. So, okay, hopefully this is, it looks good, 92% performance on that. Now we're going to take a different view, all right? We're going to take a side view of this same current. So I'm going to take this current. We now know what it is when the magnetic field lines, when they're coming straight at us. Now we're going to take a side view. All right, so go ahead and sketch this. And, just consider this to be notes, part of our notes for today. Kind of skimming over some basic stuff. Currents going to the right. Magnetic field lines are concentric circles everywhere. So we know that this current is going to be surrounded by circular field lines. All right. But now, so those circles form a plane, right? Which plane? Which tilt angle? A, B, or C? And let me start the question. Okay, question number 2. This is great. I see everybody gesticulating with their right hand. Nice. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. What's your count? Okay. And here's another one. Okay. Okay. Yeah, 90 degrees. And students, I want you to make very careful note of this because of the next question. Here's question 3. Same current, and we know the magnetic field lines are perpendicular. Okay, go ahead and vote. Another one, 69. So the electric field in the wire. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. So look. Now what you got to remember, the current I is the conventional current. Okay? And the conventional current is considered to be positive charges, and in this case, positive charges moving to the right. The electric field also points in the direction that positive charges will go. So the correct answer for this one is to the right. And which is one of the smaller. So go ahead and sketch in the electric field vector, and I just kind of put, it doesn't have to be any particular size. Now I see some of you with your right hand rule. Don't worry about that. It's the current that tells you for the electric field. Now if you're working on a magnetic field, yeah, then you want to use your right hand rule. Okay. But for just the good old electric field, the current, the conventional current, pretty much gives it to you. All right. Now we're going to do something a little different. All right. And I hope you have a good sketch of this. All right. We're going to think of this as your view, as if you are inside the loop of wire looking outward at a small, nearly straight increment of wire. Now you can see that red field line is over the orangey conductor, right? So that's inside the conductor. So you're looking out of this loop of wire, and the first thing you see is that field line, and then you see the conductor, okay? So that's a field line inside the loop, all right? Behind you so over on this side of the room, if it's me, over on this side is another, and in fact, there's wire all around the room, okay? But, directly behind me, I'm looking that way. And first thing I see is the magnetic field line. Then I see the wire. I've got current going to the right, conventional current going. And then behind me, I've got a wire and conventional current going to the right, to my left. All right, behind me, because it's It's going around clockwise. All right. But from both elements of the wire, the magnetic field is downward. So if you just think of this section that we're looking at, downward. If you think of the one behind me, downward. If you think of the one over, what is your name again? And look at Megan's. She's got some wire over there. All right, downward. Or maybe because the current's going this way, so you know. And then over here, what is your name again over here? Malia. Malia Staker. Okay, Malia's over here. She's got current over there. And it's going that way, so the field, whoa, we do it this way. The current's going that way, so the field lines where Malia is are downward. So everywhere there's downward in there. All right, now, here's the electric field. All right, now hit your refresh button because we're going to type in a word or a short phrase. Uh-oh. We're going to type in a word or a short phrase. Yeah, okay, this is good. All right, and let me go to so this is short answer. And this one, I'll be able to look at your answers carefully and grade appropriately because there might be more than one way to answer this question. All right. Describe what happens to the magnetic field B as you increase E. All right. Now think about that. Talk it over with your teammates. You guys go ahead and circulate. I'll give you a few minutes to think about it. Use your right hand rule. Use everything that you know. I hear a lot of clicking. Very nice. Matt, what's this student right next to you? What's her name? Gabby? Gabrielle. I'm glad you've got that page open. What page? That's 24.3? Yeah. Oh, it is? Oh, I thought it was. Oh, so I take it back. I know it looks like something in 24.3. So now I thought oh, what a nice industrious student. She's not looking at Facebook. Okay, 1 minute to type in your answer starting now. 30 seconds. Benjamin. Benjamin Mans. Did you do it again? Did you bring Chick-fil-A in here again? Good. Man, I didn't have breakfast the other day. That was really getting my goat. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, there's increased V. I made my E arrow a little bit longer. Now let's take a look at what you guys answered here. And let's make this big. B increases. Yeah. Oh yeah, well, okay. Expand. Ooh. Expansion of E. Now that is definitely an interesting word, but it is ambiguous. Field will grow. Flux, the flux capacitor increases. Gets stronger. Grows. Oh, here's another increase. See what else we got. Increase B. A lot of you guys are, intensifies. Oh, I like that. But you know, there's a lot of different ways to say it. All of them righteous. It gets bigger, it gets stronger, like the Bionic Man. More right? No, that is incorrect. Move right? No. Moves more right? No. Uh, I I don't know about those moving right business. Smaller is incorrect. Strengthens okay. See how there can be. This is one of the nice things I like about iClicker. You know, you can have a different word or phrase that makes sense to you, and it might be different from your neighbors, but it might be completely different. Now, do you want to see what my answer is? All right, so here's my answer. E is bigger, and there's the original B. The current is bigger, current I, and so that's my visual answer. And somebody said the flux increases. If you said the flux increases, you get an A for whoever that was. I'm not going to ask for a show of hands, but if you answered flux increases, you get the A for the day, because that is actually the best way to think about it. All right. So electromagnetic induction. And students, I want you to think carefully. What Faraday found was when he increased the magnetic field, he got some current. This exercise that we just did mentally, we increased the electric field first, and from that we got more flux lines, more field lines poking through that loop. All right. So that whole thing about the electrical field and the magnetic field changing and being, they're actually, go ahead and write down the word, coupled. They are coupled. It is electromagnetic field. It's not simply magnetism. It's not simply electricity and static, cling. It is electromagnetism. And here's the thing that we're going to be talking about till the cows come home. In electromagnetic radiation, E is almost always perpendicular to B. Now, there are some exotic, do you know any of these exotic materials where the B field is not perpendicular to the E? There are some exotic crystals and stuff, solids, where you can get something out of perpendicularity. But for the most part, they're perpendicular. So in electromagnetic radiation, so we'll assume that that's the case for everything that we do. All right, now, I want to do some calculations with you on the document cam. Can you make this chair as tall as you possibly can? All right, so let's go to the document cam. And we're going to do some, we're going to do a little bit of groaning and grunting. And then we're going to do some calculations with these. Yeah, thanks. If you're ahead of me this time. All right, so physics 2054, 10:30. Uh-oh, tomorrow's Halloween. Okay, couple notes that I want to go over with you, just to reinforce the magnetic field strength for a current carrying wire is mu naught I over 2 pi r. Now that's the first place that we saw that constant mu naught. We're going to calculate with it today, the explicit version of it. And I want to compare that to the Coulomb field, K Q over R squared. And K is the Coulomb constant. Now let's make a list of these constants. Mu naught is equal to, all right, here we go. Go ahead and write down all these, where are my specs? All right, catching a little bit of glare off this paper here. Okay, mu naught numerically is 1.256637 times 10 to the minus 6 henries per meter. And it is known in the old-fashioned terminology as the permeability of free space. And that's some 1800s terminology. All right, now the Coulomb constant is, and I'm going to give you a lot of digits. These have been measured very, very carefully to many, many digits, so that's why we're using a lot of digits. 8.9857, no, 8.98. Now, normally I just say 9 times 10 to the 9, but I'm going to use a lot more digits. 987, 5517, 887, which they've measured, and that's times 10 to the 9. And the units here, as we know, Newton meters squared per Coulomb squared, and that's the Coulomb constant. All right. And now there's another one that I think we've seen it in terms of capacitors. And, but let's do it explicitly, and that's epsilon naught. And it's all these three constants are all kind of mixed together. Here's the value for it, 8.85, 418, 78. And this one's times 10 to the minus 12 farad per meter. And this is known as the permittivity of free space. Okay, so another 1800s vocabulary phrase there. And they were thinking about capacitors when they did that, dielectrics inside of a capacitor. And same thing with the mu naught. They were thinking about inductances and stuff, putting stuff inside of a coil, I guess. So that's what they were thinking about. Now, K, Coulomb constant, there is related to epsilon naught. It's equals to 1 over 4 pi times epsilon naught. All right. So let's just do that. Let's just do 1 over 4 pi times epsilon naught. 8.85, 418, 78 times 10 to the minus 12 farads per meter. All right, and we better come out to 9 times 10 to the 9. So let's try that. Okay, I'm going to type in. So go ahead and start doing your calculation. It's pretty easy. 4 times pi times 8.854 use all the digits we got here. 8.541 878 EE minus 12 equals. Okay, now I get 1.112. Better change to scientific notation if you're not in scientific notation already. 265.0054 times 10 to the minus 10 meters per Faraday. Okay, so that's going to be the units of Coulomb's constant. All right, so that's that's the denominator. So let me put a 1 over that. Yeah, so 1 over that. Okay, so 1 over that. Now hit your 1 over button. And it should, and here's what I've got. So this stuff comes out to 8.98755 1805 times 10 to the 9. And so that's going to be Newton meters squared per Coulomb squared. All right, and that is pretty close to K up here. All right, so that looks good. I've got the first 1, 2, 3, 4, 5, 6, 7. I've got the first 7 digits on that, so that's good. All right, now there's another constant that we usually write down in a certain manner. Do you have a question, Isabel? You're just pointing to something. Okay. There's another constant, the speed of light, that's related to all of these. All right. And if you did your reading in chapter 24, you're aware of that. All right, so let's see. C is equal to 1 over the square root of mu naught times epsilon naught. Is that correct? Can you look on? I don't think it's on that page. I think I didn't write it down, but I think this is correct. Okay. So let's calculate this. And what I'm going to do, actually, you know what I'm going to do? I'm going to calculate just 1 over mu naught times epsilon naught. All right, so here we go. 1 over 1.25667 times 10 to the minus 6 henries per meter times epsilon naught, which is 8.86541.878 times 10 to the minus 12 farads per meter. All right, so let me do that, and then we'll do 1 over that. All right, so 1.25, and use all the digits that I've got, because this next one is going to be really exact. 37, 1.25, 6627, EE minus 6 times 8.854.187 EE minus 12. Okay, so this one I get 1 over 1.11264 9899 times 10 to the minus 17. Okay, now let me do the 1 over button. Okay, so now I can put another equal sign here, and that comes out to 8.987553057 times 10 to the 16. And this is going to be meters squared per second squared. I mean, if you do the farads and henries and meters, that's what it comes out to. Okay. Now, square root that answer. Here's where the money comes out. Sweet. Right now, on this one, I get the square root of that stuff, 2.99792 4792 times 10 to the 8 meters per second. And if you look up the speed of light, can you look up the speed of light on the internet? Just blow it up really big. Let's see if they have that. Yeah, go ahead. Just go ahead and do that. Switch over to that. Okay, now on the internet, it says 299,792,458. So we lost a little bit with over here after the 4. But we're pretty close. Now, I'm going to put a check mark next to that. The official value, by the way, students, this is now a constant of nature. And it's fixed. 299,792,458 exactly meters per second. And the way that so this is the official value for the speed of light. And that is now set. And so our calculations, we could have used a few more digits, I guess, in our calculations. When I did it this morning, before class, I came right on the money. I came out right to this. So I must have dropped a few digits somewhere. Anyway, we still came pretty close at 299,792,4792. So these constants that we're working with, mu naught, epsilon naught, Coulomb constant K, they're all related to the speed of light, and that is not an accident, and it's not a coincidence. Right? And it should be, obvious to you that this magnetic constant and this electric constant, they combine for the speed of light. And yeah, light is an electromagnetic wave. And by the way, I'm going to go back up here to the top. You can modify your notes. This is the same as 1 over 4 pi epsilon naught times Q over R squared. So this is the electric field with epsilon naught, and this is the magnetic field, simple source current element with mu naught, and a 2 pi R down the. And you see, there's factors of 2 pi in here, at 4 pi. Switch over to the keynote, please. Now we're going to go back to the document cam in a few minutes. The reasons that I calculated that stuff is just so that when you see these constants floating around, mu naught and epsilon naught, there's a reason for that. Now, let me ask you a mental IQ test question. What formula do you know from geometry class that has a 2 pi in it? Circumference of the circle, 2 pi r. All right. What formula do you know from geometry class that has a 4 pi in it? With what? A cone? Cone's probably got sphere, the circumference of the sphere, right? It's the circumference of the sphere, right? Is that, no? What formula? The circumference, right?
Oh, I don't know. I just know.
See, she doesn't even know. Which formula for a sphere has a 4 pi in it? 4 pi r squared. What's that this formula for? Area of a sphere. And guess what? Maxwell's equations, Maxwell's laws are all about areas and circles. Now this, I want you to look at this. You can write it down if you want, but it's not a calculus class. These are calculus formulas. They have a verbal description of Maxwell's equations in the textbook that I severely dislike, but these are the first two. Now, dA in this means a little pixel of area, an increment of area. And E times a pixel of area. What's a field times a pixel of area? What's that? What kind of calculation or concept is, the electric field times a little pixel of area? The field strength times the pixel of area. Daniel, do you remember? No, it's not a point in the field. It's a quantity that we've talked about. It's flux. B times dA, also flux. So these two laws here are flux laws. This squiggle over here, by the way, let me get my cursor. Okay, this squiggle, it looks like an S, kind of a script S, and then there's another squiggle just like it. Now that means that's what we call in calculus an integral sign, but it's shaped like an S to remind us of Greek letter sigma, which means add up. So what this equation is telling you is if you add up all the flux over the surface of a closed surface like a sphere, the number of flux lines that you capture is proportional to, I should say, to the number of charges inside that sphere. All right, so this is a law about assigning field lines and field line density to electric charges, either Q's, either positives or negatives. All right, so make a note to yourself. Maxwell's equation, the first one, electric flux and source charges. They are proportional. All right, we add up all the little fluxes in that curvaceous S for a closed surface, and that's proportional to how many electrons and protons I got in. That's it. Now, the second law down there is also a flux law, but it's the flux law for the magnetic field, B. Are there any source charges on the right-hand side of that second equation? No, they're not. It's zero. And that, my wonderful students, is why we say that there are no such things as magnetic monopoles. There is no point charge associated with a magnetic field. In other words, there's no isolated N's or isolated S's. They're zip zap. Okay? So they're both flux laws. Electric field, yeah, we got some pluses and minuses, electrons and protons, out the wazoo. But magnetic field, no N's, no S's. All right, and that's what this for. So this is a flux law, and no matter what sphere you may build, or a cube, or a pyramid, or any potato-shaped objects you may like, you're not going to capture any N's from the magnetic field line. Now, the magnetic field lines don't end on an N or an S. Now, we draw them that way, but microscopically, we don't consider them to be possible. All right, so here's your source charge. Go ahead and make a note of that. Q is the source charge. And but down here, we don't have zip zap for a source charge on the similar looking magnetic flux. So the left-hand side of each of those equations is something we've already done. Flux. The flux capacitor. All right, we got a flux for magnetism. We got flux for electricity. All right, but magnetism, we don't have any source charges. What's the source of the magnetic field? Moving charge. Okay, so we don't have a moving charge. This is kind of a static law, both of those. All right. Now I'm going to push those over to the side. Get them out of the way. And let's look at two more of Maxwell's equations. Now this is a little bit different. Here's the other one. Okay, now this one is related to a closed path. So on this one, the little element ds, that's like a pixel. No, that's like a little teeny line segment of a given path. This is called a path integral or a line integral. All right. So you count up. This basically tells you count up all the electric field strengths parallel to the path. All right. And what that's going to give you is the time rate of change. Now on the right in the top equation, d phi over dt, that's like delta phi over delta t, only that's the calculus way of saying it. All right. And that's your change in flux over time on the right. On the left, that is like the voltage. Because remember from when we did work in physics 2053, it was the component of the force parallel to the trajectory that increases or decreases the speed. It changes the kinetic energy, either decreases it or increases it. And the same thing here. Now that's a voltage. So voltage is similar to it's like a cousin of work and energy. All right. So on the left here, you have the cousin of good old F delta X or F delta S on the left. And on the right, you have the flux. Flux is in this one too. Oh my goodness. Flux capacitors. No wonder this is the key to time travel, because it's all over Maxwell's laws. Now the second one is similar. B and ds, that's what we call a line integral there. And now we're counting up all the components of B that are parallel to the circuit, if you want to think of it that way. And on the right side, we have some sources of current. We have mu naught times I. Now there, let's see. Here's my EMF over here. This is, by the way, this one up here in the upper right, that's Faraday's law, basically, written with calculus. Now that's not the way Faraday thought of it. I mean, he thought of the right side, okay. He didn't think of the integrals and stuff, all the calculus on the left side. And neither did we. But that's what it is. And then down here, this one, look, there's the magnetic flux through a surface. So there's some more flux. And that kind of squiggly looking d over dt, squiggly looking d over squiggly dt, that's a time rate of change as well. And notice what we got in there. We got a c squared in the denominator. Nice. And we also have another source term for the magnetic field, and that is mu naught I, the current. And so this one, they use Walgreens Pharmacy's calling. So that's a source term over there. All right. So we got source terms, but they don't come in exactly the same way. But those are Maxwell's equations. All right. Now let me repeat. Nobody in here except for Brandon and Thomas have to work with these calculus equations. And that's because Thomas tries to trick me every day with the left-hand rule symbol. But otherwise, you guys don't have to worry about these. But that's what they are. You've taken a look at them. I've described them in terms that make sense to what we've already done. Sources and flux. Flux, we've got flux. Flux is the hard part. Okay, that's the part that Faraday figured out. Now, here's this. Sorry, I'm about to puke because of this stuff. It is It is, as my son would say, this is nasty. All right. So, but you might like it. So go ahead and look. I mean, it's a verbal description of Maxwell's equations that if this were if this were a undergraduate physics major class and I put this on the board, there'd be like an insurrection. You know, they'd instantly rebel, and I rebel against this. But it's in our textbook. You might enjoy reading it, and I commend it to your further education. Now, what we're going to start talking about is this waves, electromagnetic waves. Now, I said before that the magnetic field and the electric field are perpendicular. Over there on the left, you have two rods, and then between you have a squid or a fluke, I should say, and it's got a squiggle indicating that it's a source of alternating current. So the charges are shuttling up and down, up and down. They're oscillating up and down vertically. And in the axis that is shown, the electric field marches off to the lower right. This is figure 3 of chapter 24.2, by the way. Let me see if I can get that over here. The magnetic field is red in this diagram, and if you look up electromagnetic radiation and the word perpendicular on Google or something, or Yahoo, you'll see buku images like this. I mean, it's a standard image. And this one's pretty nice. And it emphasizes that the blue electric field vectors, they're varying in size. And they're propagating out to the lower right at speed c. So that green arrow is the velocity of propagation. And the red arrows, those are the magnetic field. They're perpendicular to, look, look at that's what we call a dipole antenna. All right. A source of alternating current, and the electrons shuttling up and down, up and down, up and down, and they produce radiation like this. We call it dipole radiation. And in this direction, it would look like this. And the magnetic field is perpendicular. It's perpendicular to the antenna. All right. The electric field's in the same direction as the antenna. But the magnetic field is perpendicular to the antenna, and it wavers left and right. You can see the first bunch is left, the second bump in the curve. Oh, and by the way, those are sines and cosines. Okay? Sines and cosines. In fact, those are both sine curves. If you take the very left part of the E and B planes to be the origin, those would be sines and cosines. Okay? So the magnetic field is in the is in the horizontal-ish plane, and it's going to the left, it's going to the right, back to the left, and so on down as it propagates out to infinity. And the electric field is perpendicular to that. It's going up, it's going down, it's going up again at various magnitudes. All right. And those magnitudes are in sync with the behavior of the electrons in the source, in the antenna. Right? Now, there's something else I want to go over with you, and that is the magnitudes of the electric field and the fact that E over B is equal to C. Now, I'm going to go to the document camera. See, I did that myself. That shows you how good my back is. All right. And I'm going to go down here to the document camera again, this time without groaning. And we're going to do a little bit of messing around with E and B. All right. Now, so this is page 2 from the document cam today. All right, so let's think in terms of newtons. Newtons of force. And we know that the magnetic force is equal to QV cross B. And I'll make that into a vector statement. Okay, so QV cross B. And we know that the electrical force is equal to KQ1 Q2 over R squared times the R hat vector. Okay. Now, so let's modify this to Q times E. Okay, so that's also, you know, electric force. And let's use this one. Okay, so we know that, and in fact, this is more general. Okay, this is for a point charge up here, but in general, whatever the electric field is, multiply that by your test charge or your device charge, and then that'll give you some newtons. So this stuff over here is newtons, and that's equal to a coulomb. It's Walgreen. I'm going to have to let it pass. Okay, so this is Q times speed times B. And then this is newtons are equal to Q times an E. All right, so that means QVB is the same units, units of, okay, are equal to QE. Now cancel out Q, and you get VB equals E. And so when you work out all the constants and stuff, this is kind of loose right in here. But when you work out all the constants and stuff, you get speed of light is equal to E over B. All right. And so this ratio here is basically a fact that we have Q times the velocity over here for the magnetic force. All right. And whereas over here for the electric force, it's just Q times the field. So, all right. So wherever we see E squared, for instance, in a formula, we're probably going to see a C squared times B squared if symmetric. Oh, wait a minute. Did I say that was possible? Yeah. This is the energy. The energy in the electromagnetic field. This is actually the energy density. Is proportional to E and B squared, right? And what did I tell you about stuff where you find squares in the energy equation? What is that a sign of? Squares in the energy equation. So you got to sing it. No, you have to sing it. Oscillation, oscillation, oscillation. You know, I used to sing in the choir, but my voice is so out of shape now. All right, so yeah. So my wonderful students, we're heading this way. And it's another sign that, oh, and by the way, this ends up being the speed of the speed of light is automatically in the oscillator energy equation here. And guess where it was? We didn't really work it out. But when we had this for oscillators, spring system, 1/2 kx squared plus 1/2 mv squared, the oscillator frequency was related to K and M, and so was the maximum speed, also related to K and M by a bunch of square roots and stuff. So it was all in there. I don't think we went over it in 2053, but we could have. And we are going to be going over it in 2054. So it's pretty sweet. Now, and it equals MC squared, yeah. That's even more mysterious, but it's cool. Oh, actually, you know what I'm going to show you, as long as we're on the topic of relativity, let me show you a space-time diagram. So this is 3. Okay, now a space-time diagram is something that you have to use in relativity, and it's similar to XY diagrams, except one of the axes is time instead of coordinate distance. So we'll use X for the sideways coordinate axis. And then up here, we'll use time. And because I want to have distances on both axes, I don't want to mix apples and oranges, I'm going to multiply this by good old speed of light, c. So that means that this vertical axis is distance, like in the units of light years or light seconds. You know, the speed of light times the time is a distance. Okay, and so same thing here. So if you think of everything in terms of light years or light seconds, then you're good. Now, let's go 1 light second out, 2 light seconds out, and I'll go 3 light seconds out. Okay, and then we go 1 light second here, 2 here. Okay, I'll go up 2 light seconds here. All right. Now, put a dot here at the origin. Okay, 0, 0. Now, a photon of light will travel this far in 1 second. So go ahead and make a dotted line out here. Okay, so here's where a photon of light would go, from here to here. And in fact, I'll go out here, 2, 2. And in fact, and I'll write it in red. This is the photon line, or what we call the null surface, or what we would call a null surface, if it were 3 dimensions instead of just 2. All right. Now, can anybody here, in 1 second of travel, can anybody here go further than 1 light second? Raise your hand if you can. But if you're the Flash, don't tell me that. But anyways, I'm just kidding around about that. In general, a person or any other physical system is not going to be able to go any faster than this. So to go 1 light second might take 2. So write your name there. You know, if you go, if it takes 2 seconds for you to go 1 light second in distance. So this is you here. All right. And everybody, physical system along the x-axis anyways, is inside this wedge. And if you're going backwards, you know, let me extend the x-axis over here. If you're going backwards, here's your photon line for leftward going photons. Okay, so these are 40, these are basically 45-degree lines. So this is 45 degrees. This is 45 degrees over here. Okay. So every physical motion other than photons other than photons is inside that. So this zone here is kind of 40 between the 45-degree lines. That's what we call a light cone. So and to see what it would look in 2 dimensions, I'll just draw a 2-dimensional version of. Okay, so here's X, Y, and CT. Okay, so there's a 3-dimensional view. And the light cone would look about like this. And it would just keep opening outwards. All photons are going to be on, no matter what color photon you are, no matter what your state of motion, you're going to be on this photon surface. So this is a light cone. All right. And so the electromagnetic, this is where the electromagnetic field, the electromagnetic radiation domiciles on this line, on that photon line. So, and here's us, you know, poking around. This is you guys. I'll erase the word me and I'll put yous guys. All right, now here's me trying to get up the stairs, just kind of poking along here. There's Dr. B. For now, I'll be back and ready to roll in just another few weeks. All right. So anything, and here's somebody going to the left. Christine. This is Christine at the bell right here, blazing almost at the speed of light in the opposite direction. She's leaving the class. No? Not quite. Okay. Anyways, that's somebody going to the left at a good speed. So that's just a little bit of enrichment for you, and because I'll be as we go through all this lecture about light and speed of light and the spectrum and stuff, I'm always thinking, this is always the thing that's in my mind, is I'm always thinking in terms of 4 dimensions. All right, let's go back to, you want to switch me back to let's stay here for now. All right, now here's another image of a dipole antenna. And this is what happens when you receive electrical radiation. So there's some, there's a radio station, Z88.3, or whatever station you listen to, and it sends out electromagnetic radiations. And when it hits your antenna, it causes the electrons to go back and forth in the antenna, and then it's amplified, and it's on an LC. You can see it's on an LC circuit, And that little arrow down here in the LC circuit means that it's a tunable capacitor. All right. Now, in the olden days of the first transistor radios, you had this big, gigantic capacitor, and you had to turn this dial in order to change the position of the wire lead on the capacitor, thereby changing the capacitance. But that's how you tuned in a radio. Now we have electronic tuning; it's much more accurate. But this is the tuner down here. All right, so you tune this, and you change C, and that changes the frequency that's picked up. And then so you change to the frequency you want, and then when you get it, it'll couple over to this other circuit through this inductance, and then that'll be then it'll go through the amplifier and out through the speakers and stuff. Now, can you, James or Andrew, can you switch to the main computer, please? On your the press books on our free textbook, this is at the bottom of which one is this? This is 224.2. At the bottom of 20, no, go back up to that highlighted area. This is I really, really recommend this simulation to you. All right, and it's outstanding. It works really, really great. This is what it looks like. Go back to the okay. Here's what the simulation looks like when you open it up. You have to download a Java file, and then you have to open it. And if you're on a Mac, you have to give it permission to open and stuff. Or you could maybe, I don't know if you could do, can you do that at the library? Do they let you download Java files at the library? Probably not. Probably only work on your computer. But the link on that page that you just saw is good. You'll link to it. And hey, you guys, what I highly recommend, actually, let's see if we can do this thing. See if you can do that. What I highly recommend, no, hit the link down there. There we go. Go ahead and download it. I highly recommend using the radiated field. All right, see that little arrow down there? That is pretty sweet. It's working. All right, let's switch to this. All right, here we go. Andrew comes through. Now here's the simulator. So what you do is you rattle the electrons in the transmitter. The transmitter's, I'll operate this. The transmitter's over here, right? Okay, where it says KPHT. So you just go, and it sends out a signal of electromagnetic fields. Now that's the radiated field. All right, and you can just do curves, and you can see that's the amplitudes, and then the full field is. This is kind of cool watching this. And then the other thing that's interesting is you can see the electron positions in the transmitter and the receiver. So let's do that last one, and let's see what happens to now the receiver is down here in this lower window. So let's see if we can do a little. Okay, there it goes. Yeah, it's not, dude. Let me make it a little bit bigger. Dude, it's not doing jack. It's not doing jack at the, you can see the thing move a little bit, but let's try this. Yeah, this is kind of slow. Now you can see the electron moving. See over here in the receiver? All right, it's a pretty big amplitude. Let me make the amplitude a little bit smaller. Let me increase the frequency. That's pathetic. That's like Grandma Moses. Here we go. All right, so you get some, let's jam the amplitude up to maximum. Dun, 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 dun. Now we're getting some, that thing's getting jacked up there. Anyways, this thing is, now here's just manual. Of course, flatline. It's dead. All right, so let's just do a little bit of, there's a little pulse. Let's see what happens. You know, it's pathetic. This thing, I don't know how they do it, but anyways, you can fool around with this. And, oh, there's a help button down here.
I think what's happening is you're going so quickly, it's getting all of it at once, so it's balancing it out on the side.
Yeah, it's sampling too. Yeah, let's try that. Let's try that. Let's try it. All right, let's see if I can do this a little bit more slowly. Phew, look at that. There it is. It's that little blip. All right. Well, this antenna's not very responsive, I guess. All right. So you want to switch me back to the. Okay. Anyway, so I hardly recommend that you mess around with that. And you know that website, the University of Colorado, they have a ton. They have a metric ton of other simulations that are pretty nice. All right, let's talk about the electromagnetic spectrum. Now, this is a diagram. I don't know where I got this, but there's some diagrams in the textbook too. If you look in if you type in electromagnetic spectrum in Google, you'll come up with 60,000 different versions of this. Now, this is good. This one's arranged from long wavelengths on the right and small wavelengths on the left. Or excuse me, long wavelengths on the left and short wavelengths on the right. So look over here, gamma rays. This is the stuff that made the Hulk out originally, gamma radiation. 10 to the minus 16 meters, that's really small. Here's 10 to the minus 12 meters. 10 to the minus 9 is right here. X-rays, that's a nanometer. The size of an atom is right about here. 10 to the minus 9, 10 to the minus 10 in this area. So this is why X-rays can be diffracted by crystals. They'll go through a crystal and diffract like they'll turn into a rainbow, or they'll diffract, right? X-ray crystallography. All right. Now here's ultraviolet. Now this one's down in the it's shorter wavelengths, 10 to the minus 6. All right. And then here's visible light, this real narrow band here. Now go ahead and write down. I'm gonna turn on the document cam one more time. And I'm gonna give you the name of a very famous physicist who donated his name to science, Roy G. Biv. Go ahead and write this down. Roy G. Biv, very famous scientist, almost as famous as Avogadro and Avogadro's number. Now, Roy G. Biv is famous because the color sequence for the visible spectrum corresponds to the letters of his name. So his parents, when they gave him the name Roy G, they were, So here it is: red, orange, yellow, green, blue, indigo, violet. The Roy G. Biv effect. Well, if you want me to make a Roy G. Biv test, I can do that. But the thing is, can you withstand the punishment? Because Roy G. Biv, what does Roy G. Biv mean? That's one or two questions. But then if I have to make every question I want to put on the test with Roy G. Biv concepts, oh my, our GTA here was absent on Monday because he was doing a thesis defense. I read one time, or one of my professors in grad school told me, he went to the University of Chicago, and they gave him extremely difficult questions on their PhD exams and their PhD defenses. Because when you're defending your thesis, you have this paper that you write, and then you defend it, and then when they're satisfied with that, then it's open season. They can ask you anything, any physics question they want. Is that what happened to you? So they ask you any. So he said, yeah, I've been in meetings where the defense, the question was, the sky is blue, derive Planck's constant. So that's a Roy G. Biv question. The sky is blue. The sky is the fourth letter of Roy G. Biv's name. Derive the value of Planck's constant. That's savage. Anyway, now it's an ultraviolet catastrophe. Okay. Now, can you do me a let me turn off my mic here a second. I want you to go on Google, get Google Maps, and look up Clam Lake, Wisconsin. Okay, and get a satellite view. Okay, so now a couple more comments here. Infrared, that's at a longer wavelength than Roy G. Biv. Oh, by the way, Roy G. Biv, the wavelengths are for red, 700 nanometers, for violet, 400 nanometers, approximately. Okay, so go ahead and jot that down in your notes. If I ask you something in between 700 and 400 nanometers wavelength, then you know it's visible. Okay, if I ask you for something up above, lovely. If I ask you for something up above, can you give me the side panel? Good. All right. If I ask you for something above 700, then you know it's infrared. Okay, and it's down here. Now, a couple things about this. See this up here, microwaves? One man's microwave is another man's infrared. So there's no solid boundary. And in fact, Roy G. Biv is kind of, approximate. Somebody in this classroom might be able to see 702 nanometer, whereas somebody else might not. And the same thing with violet. They might be able to see 394 nanometers and other people not. So radio waves, now down here, look at this wavelength, 10 to the 4. That's 10 to the 4 meters. That's 10 kilometers. So it's about 6 miles. Now, you know what these are radio waves. You know what they do with this stuff? They communicate. The U.S. Navy has big transmitters like this one up in Clam Lake, Wisconsin. Come on, baby. All right. And then another one over on the Michigan Peninsula, the mitten of Michigan, where they have these ultra long, or what they call extreme low frequency transmitters down in this wavelength band. So they have to have huge transmitters, miles long. And if you look at Clam Lake from the satellite view, you can see the traces. It's dismantled now, but you can see where it used to be if you look carefully at the map. And they would transmit signals to submarines at sea underwater. Now, during the Cold War, before most of you guys were born, but back in the old days, when I was in college, we had to worry about the Russians. And we don't worry about them like we do today, but in those days, we had to track the Russians, and we had to hide our missile submarines from the Russians. And the way that we did that was just making them ultra quiet. And This radio frequency, ELF, they call it, extreme low frequency. Um, and they have transmitters in Hawaii and stuff, various places. They have some in Scotland. They have one in Maine. The most powerful radio station in the world is on the east coast of Maine, almost up to Canada, facing out into the North Atlantic, because that's how they communicate with submarines at sea. They're very slow. It's a very low frequency, so the data rate, it's not like your phone where you have a lot of gigahertz of bandwidth. This thing, look at the bandwidth on this. The frequency, 10 to the 4 hertz. That sucks. That's worse than dial-up. So this band, the advantage of it is that it can penetrate seawater for a decent depth. So a sub can be hidden, but because the data rate is so slow, all they can do is signal the name of the submarine and then please come to the surface, and then they put up their regular antenna and they get instructions. But that's ELF. And all through here, microwaves. This is where we have radar. Okay. Also, microwaves is where we have cell phone. Your cell phone signal is in the gigahertz. See, here's gigs, 10 to the 8th. Here's 10 to the 9 frequency, 10 to the 9. So that's gigs in here, right in here. All right, microwaves. And then here's even higher frequencies. Your microwave oven. But radar, millimeter band radar is right about here, 10 to the minus 3, and various missile radars and stuff are down here. All right. And so, you use all these different wavelengths for all kinds of different applications and stuff. I was reading about these extreme low frequency, what they do? They use them to communicate all over the world. They transmit, the Earth is charged, and there's a layer of the ionosphere that's also charged, ionosphere. And so and it just so happens that at certain frequencies of ELF, they can transmit all the way around the world between the two charged layers like a waveguide. So it's pretty cool. So it's like it totally channels, thousands and thousands of miles away, way more than any other, band. Shortwave radio is down in here somewhere. I don't know too much about shortwave. Here's AM and FM. Okay. FM is 100 gigahertz or 100 megahertz, and here's AM. That's a few 100,000 hertz. So now astronomers observe in most of the bands. Now we have to, for some things like X-rays, we have to go above the atmosphere. But this one here, let's see what my notes. I don't have my notes on this one. This one is a composite of X-ray, optical, and infrared. This is the famous Crab Nebula, which is a supernova detonation remnant from about 1,000 years ago. The first observed by the Chinese and some Europeans saw this supernova about 1,000 years ago, and this is what it looks like now. It was a big detonation, a big bright star in the sky, so they call it nova. Now, let's look at some of Maxwell's ideas before we dismiss. Okay, waves. Faraday's law of induction provides part of the basis for the radiation field. This law describes the EMF, or potential difference, produced by a changing magnetic field. All right. Potential difference can be related to an electric field. Thus, a changing magnetic field produces an electric field, and vice versa. Now, this is what we talked about at the beginning of class. Maxwell predicted that the reverse effect also occurs, namely that a changing electric field produces a magnetic field. All right, and that was Maxwell. Here's a picture of Maxwell with the James Harden beard, ZZ Top. So now you know why ZZ Top you know, they didn't invent it. It was Maxwell. So anyways, this is the guy that predicted it. And then as we talked about last time, Hertz is the one that actually observed it for the first time. Now, a couple things about this. Look at these notes. A changing magnetic field. Now that's delta B over delta T. All right. Also, a changing electric field. That's delta E over delta T. And what happens is there's a gradient in the electric field or a gradient in the magnetic field. So that's delta B over delta X. It changes with position. All right. And so what you get are equations that look like this. Now go ahead and write these down. Delta E over delta X is equal to minus delta B over delta T. And the other matching equation is delta B over delta X equals minus mu naught epsilon naught times delta E over delta T. Now, on the left, so these are basically the last two of Maxwell's equations. But now instead of looking at surfaces and stuff, we're looking at slopes. We're looking at, rise over runs of the field variations. And notice that we have mu naught epsilon naught. And so the speed of light is going to be in here. So you have a system of spatial and temporal variations. And here are the spatial variations over here on the left. That's delta E over delta X, and then down here, delta B over delta X. But notice the other side is a delta something over delta T. All right? And that's a temporal variation. So that's what this one is. And then this one. And don't forget that mu naught epsilon naught is 1 over c squared. All right? So whenever you see some kind of a delta something over delta x coupled, now these two equations are coupled. Make a note of that. These two equations are coupled. They both involve E, they both involve B. So they're coupled. So if one of them changes, the second equation is going to change. All right, so they together, those two equations, if you see some spatial and temporal variation in two coupled equations like that, bam, you always have a wave equation that comes out of that. So, that's a whole lot of space-time trigonometry in those two things. That's all right. The wave equation that comes out of it is extremely simple. C equals lambda F. There it is. That is the electromagnetic wave equation. And C represents the speed of light. We already calculated that. Lambda is the wavelength. F is the frequency. So lambda in meters, frequency in hertz or seconds to the minus 1. And that's your equation. Now, next time we're going to do some calculations with C equals lambda F, and I want you to finish reading all of chapter 24, okay? And I'll try to finish annotating that. Now you're dismissed.